Well, hello there, everybody. I thought we'd start tonight off with a little joke, and I'll have another one at the end, so stick around. So the opening joke is, what did one toilet say to the other toilet? Any guesses? You look flushed. That's pretty good, isn't it? All right. Well, today in this video, we're going to talk about a couple things that kind of move us forward in this unit of geometry we've been doing. The other day we talked about etymology, and that means the origin of a word. And so I want to talk about a word that we're going to use in this video called isometry. Isometry comes from the Greek. There's two words, iso, which means same, and meter, which means measure. So isometry means literally same measure. Okay, and now I want to talk about these two words here, congruent and equal. Now, these two triangles, the blue one here and the green one here, are congruent to each other, but they are not equal to each other. So the difference is that congruent means when two figures have the same size and shape. So these two triangles are congruent to each other because they have the same size and they have the same shape, but they are not equal to each other. So congruent is two figures have the same size and shape. Now, if I say that two things are equal, what I'm saying then is that these two things really are the same. So, for example, if I say x equals 2, then I'm saying that x and 2 are the exact same thing. But in the case of these figures, this blue triangle and this green triangle are not the same exact thing. They are two different triangles. This one is blue by itself, and this one is green by itself. They're not equal to each other. In other words, I can't just put this green one in place of this blue one or vice versa. But they are congruent, meaning that they have the same size and the same shape. Okay, so I want you to kind of grab that distinction. Make sure you get that. Okay, so that's the second thing. Now, let's talk about this isometry deal that we began this video with. The first isometry that we're going to talk about is a translation. And a translation is a horizontal or vertical shift. All right, and so what we're going to do for a translation is say we have, for example, this figure right here. I want to translate it this far. So this line right here is going to represent how far I want to translate this figure. From this point to this point. So I'm going to mark that, and then I'm going to take all of this and I'm going to translate it that far. Okay, so notice what happened. This figure is the same size as this one. It's the same shape as this one. The difference is that it's in a new position. So this is an image of this one. So whenever I perform an isometry, I'm taking this original shape and I'm doing, in this case, a translation. I'm moving it, in this case, horizontally, and I'm creating an image. So this figure here, which I will color with a different color so we can tell them apart, this red one is an image of this purple one. They are congruent to each other, same size, same shape. Notice also that the distance between every set of points, every corresponding set of points, for example, this point and this point are corresponding points because they're in the same position on both figures. The distance between them is this marked distance that I used. Also between these two, and between these two, and these, and these, and these. Okay, so that's a translation. This is an image here. So if I labeled this point, say with C, this point we say is C, and it's hard to see, but there's a little C prime, there's a little apostrophe there. And that means, I'll make it a little larger for you, C is the original and C prime is the image of C. So C prime is the point that corresponds to C in the image of the original figure. Okay? Alright, now the next isometry that I want to talk about is called a rotation. A rotation also preserves size and shape, and so a rotation is turning a figure around a specific point a specific number of degrees. Alright, so let's take this figure and let's do a rotation with this figure. So I'm going to move it down here just a little bit. So this is the point that I'm going to use as my center of rotation. So this figure is going to rotate around this point, and let's just say for now we're going to use 40 degrees. So I'm going to rotate the figure 40 degrees. I'll make it a little bit bigger than that to make it easier for you to see. 100 degrees. Okay, so this figure has been rotated 100 degrees this way. To show you that it's a rotation and not a translation, I'll show you some circles here. So if I go from this point to this image on the original, notice that this point is on that circle also. If I go from the center of rotation to this point, notice that its corresponding image point, which would be here, is on this figure. So imagine how this would look. It's going to rotate up like this. Okay, so this point right here moves over and becomes this point right here. So it looks like it's reversed, but it's been rotated. If I take another circle and connect this original image point right here, notice that it, from here, has been rotated around to here. Okay, so we've rotated this figure around. Also notice if I make an angle between any point and its image point, remember the image point we talked about just a minute ago, the measure of this angle, as you might guess, should be 100 degrees because we rotated this figure 100 degrees. So if I measure this angle, notice that I do get 100 degrees. Okay, and that's what we said that we wanted it to be rotated at. So if I go from here to its image point, which would be here, that should be 100 degrees. If I go from here to here, that should be 100 degrees. Okay, now the last isometry we're going to talk about is called a reflection. And just like in the mirror, if you think about how that works when you look in the mirror, a reflection is a kind of a backwards or an inverted image of the original. So if this is the original figure, we're going to reflect it over this line. So this line is going to become like a mirror. So I'm going to take this figure and I'm going to reflect it over that line. Notice that it's the opposite. It's like I took the figure and flipped it over this line by keeping this side facing the line of reflection. So here, this side faces this line, and if you imagine in a three-dimensional world, this is like a two-dimensional plane here. If you imagine in a three-dimensional world, if I kept this figure, this side of the figure facing this line at all times, then to reflect it is to move it over here. Now this side, which is the image of this side, is still facing that line. Okay. Also notice that if I measure the distance from here to there, and from here, which is its image point, to there, they should be equal. And if I measure them both, I get the same thing for both of them. Okay, so from F to G, which is here, I got 2.76 centimeters, and from G to F prime, remember that's the image of F, I get 2.76 centimeters. So the distance between the line of reflection and the images at any point on the image should be the same. All right, and that concludes today's video. I hope you enjoyed it. Oh yeah, your joke. Okay, to close you out for the night, what did the lawyer name his daughter? Sue. That's pretty good, isn't it? See ya.